Multi-resolution analysis. As you know, we defined it earlier. And let me just refresh your memory on what that is, and then we'll go ahead with the material. So, okay, so recall the definition and MRA, multi-resolution analysis of L2 of R is a sequence of closed subspaces. By that I mean vector spaces, sub-vector spaces, linear spaces, spaces of L2 of R, and we're going to designate this sequence by Vj, J in all the integers. And a function phi in L2 of R such that the following conditions hold. Namely, for all j in Z, Vj is contained in Vj plus 1. F belongs to Vj if and only if for all k and z, the translate by k of f is also in Vj. And C, f belongs to, let me write suggestively here, f of t belongs to Vj if and only if f of 2t belongs to Vj, excuse me, Vj plus 1. D, the intersection of all the Vj's is the zero function, and the union of all the Vj's is equal to L2 of R. And then E, the tau k phis, that sequence is an orthonormal basis for the closed linear span of tau k phi, and that is what V0 is.
On D, that's the closure of the union?
Yes.
Okay.
You know, it won't be the whole thing in general. You have to close it up. So let me just say something about generalization first of all. So there's nothing sacred about the number 2, although some numbers, I mean, it's a great number. But certainly other scaling factors are used. And besides other scaling factors, one wants to do wavelet theory in other spaces besides L2, and one can in many spaces. In fact, because of topics in harmonic analysis and partial differential equation, there are spaces out there that you can shake a stick at, and one of the great features of wavelet theory is that looking at this phase problem that I sort of alluded to, looking at the absolute value of coefficients can help you know when a function is in a space or not. That's not the case sometimes with Fourier analysis. So one generalizes in that direction. Different spaces, different scales, and in this multi-resolution phenomenon. But also, one makes wavelets when you don't have a multi-resolution analysis. And that's also a big deal. It wasn't such a big deal initially, but it's becoming more of a big deal. And then there's higher dimensions where naturally you want to do wavelet theory, I mean Euclidean space. There, the types of scalings you use for multi-resolution analysis, the sky's the limit. I mean, because then you start using matrices that have certain properties. And this hypothesis here, orthonormal basis, there's nothing sacred about that. By the way, that just reminds me, I went to a Jesuit college, and I'm proud of it. But and then when I went to Harvard, a lot of people thought I was really going to lose my soul, which I might have. I don't know. But anyhow, the Jesuit college, we took a course in ethics, senior year. We had a Jesuit teach it. In fact, this Jesuit was a man by the name of Father Rock, who was associated, a relative of a scientist, or a close protege of the scientist who invented the pill before the new the pill. I'm on television here, I can't deal with every detail. In any case, I remember our class was all men, and when we would talk about some of these things in ethics, he would take off his Roman collar and he'd say, there are certain things you don't die about, gentlemen. So we're not going to die about, we're not going to, it's even easier to say about this stuff here. We're not going to, it's very interesting, but I'm just telling you all the different generalizations. So in higher dimensions, you generalize by, instead of having then a matrix with just 2's down the diagonal, you have different types of matrices for which it works, which means you're dealing with different sorts of filters, because this ties in very nicely with filters that arise in coding theory and engineering. And then you're not only just interested in RD, you're also interested in locally compact groups, and a lot of work has been done on that. And some groups are more like RD than others, and the ones that are the antithesis of RD are essentially local fields, or basically compact groups with, basically groups with compact open subgroups, which RD doesn't have. And that's of use in number theory. And once again, you can do all of this stuff in the non-multi-resolution setting. And this thing about, I'm coming back to it, this thing about you don't even need this as a hypothesis. You can assume that you have a re-spaces here. You don't even need that. You can assume you just have a frame. And if you have a frame, and of course you don't get orthonormal bases anymore, and you don't with the re-spaces either, but you can still construct wavelets. So the realm of generalization is very, very broad, and a lot of work has been done on all of those topics. However, having said that, I like to think that there are really two big distinctions, multi-resolution analysis and non-multi-resolution analysis, because those are conceptually quite different to a certain extent, because even there's now a theory of generalized multi-resolution analysis, which sort of combines things, but at a certain level they're distinct. But if you're interested in the multi-resolution analysis realm of things, then if you do this carefully, and if you're quite good technically, then a lot of these other things fall in place. If you understand the concept here, it's a very similar concept. Now, particular applications are quite fascinating, because once you start coming up with certain of these filters that are in higher dimensions that are not formed by tensor products, that's quite exciting. So there's lots of exciting things going on in some of these issues, but in a first semester course, this is what we're gonna do in one dimension, okay? And the main theorem, once you have this definition, and I already talked about how its origins from speech processing and image processing, so I shall not repeat myself. But the main theorem in this realm is the following. Let Vj phi be a multi-resolution analysis of L2 of R with, we call these functions phi scaling functions, with scaling function phi. Then there is a constructible function psi, which depends on phi, such that psi mn is an orthonormal basis for L2 of R. And so we're going to prove this theorem. And two examples we know right off the bat of multi-resolution analyses. And I'll show you the how one later, but we already showed the Shannon one, our Har and Shannon.
Is the converse true?
What's the converse?
So if you have the other function, you get. So there's.
Can you make a multi-resolution analysis? So if you've got a, well, how would we pose the converse here? I mean, if I have an orthonormal basis, just like that, does it come from a multi-resolution analysis? And the answer is no. If you bring in some sort of function, then you'd have to have some properties, so maybe that's something to think about a little bit offline.
It's like compactly supported or something.
Well, no, that he wasn't saying that, but in fact, that was what I mentioned with Bill she did. She pointed out that you can find, I didn't phrase it in terms of multi-resolution analysis.
Right, so if you have this one function, you can always find a scaling function, but if you have a scaling function.
If you have a scaling function, this phi is called a scaling function. If you have a scaling function, you can always find psi, which is called a wavelet. There are wavelets which do not come from multi-resolution analysis. So, the thing about the continuity is, Bill Bashiz did not phrase it in terms of multi-resolution analysis, but that is multi-resolution analysis. And that's basically that you can find very smooth functions which are compactly supported, which are wavelet orthonormal bases. I mean, that was the rub on Har, but it wasn't smooth.
Is one of these called a seed function?
Well, they use different names, a mother
Okay.
function and father function.
Right.
I'm not going to get into that. I'm going to call this a scaling function because there are scaling equations to solve, and might not call it anything. And this is the wavelet.
Okay.
Is the scaling form equation, is that
Yes, the scaling equations we solve.
possible?
Well, we're going to do that. We're going to do. Okay. This is the theorem we're going to prove. Given a multi-resolution analysis, we can prove this theorem. And just as examples, Har, which I haven't shown you it's a multi-resolution analysis, because there are things to prove there, to be shown. And Shannon, shown. multi-resolution analysis wavelet systems. Okay. The first thing I want to talk about tonight on this subject, no, it won't be the last, but is let's look at this item E. And the I was complaining about the soft chalk, and now this is like Little Red Riding Hood. This was too hard, so I'm never satisfied. Let phi be in L2 of I. And define function phi of gamma to be equal to the sum of phi hat of gamma plus n squared, n running through all of z. Now, you know, I've developed, I mean, this course, this semester, was developed from the point of view of the sampling theorem, where we have this mixing, this wasn't just an accidental mixing of Fourier series and Fourier transforms, of discrete subgroups and periodizations to make things work. And that's in some sense a continuing theme. And in this case here, what we have is the following. Note, phi belongs to L1 of the torus. And a lot of things I'm going to say for the rest of the night are true in RD, but I'll just state it for our. Phi belongs in L1 of the torus by Beppel-Levy. And Plancherel. And I'll let you do that yourself.
What's Beppel-Levy?
Beppel-Levy was an Italian mathematician, that's his full name. And he emigrated to Argentina. He was a professor in Argentina for a lot of his senior years in Rosario, in Argentina. And the Beppel-Levy theorem is part of the cadre of theorems associated with Lebesgue-dominated convergence theorem. And frequently it's associated with increasing sequences converging. And you see we'll have increasingness here because of, if you take finite sums, everything's positive and you let them get bigger. So that's the hint. But anyhow, let's do an interesting calculation. I'll call it a theorem, but it's an elementary calculation, really. Let phi be in L2 of R. By the way, it might be amusing for you to sort of intrinsically characterize when this guy here is actually an L2. I mean, it's easy to prove it's an L1, but come up problem, put it down there, Nate. Find examples when it's not an L1, when it's not an L2 rather, and then intrinsically characterize when it is an L2. So let phi be an L2 of R, and let V be equal to the closed linear span of tau k phi. Okay? And then, so that's a closed subspace of L2 of R. Then, fact, this guy here, tau n phi, is an orthonormal basis for V if and only if phi is equal to 1 almost everywhere. That's pretty interesting. It's even more interesting considering how easy it's going to be to prove. So you can see, and these things, there are several other things that are really related here. The Zach transform, there are other things that we'll talk about eventually, but let's just verify this proof. So it suffices to prove, since I have this is in the span, I just have to prove that orthonormality and 1, excuse the pun, are 1 and the same. So let's just calculate. We look at phi of t and phi of t minus n dt, and then I'm going to use Parseval. If I use Parseval, then what I get is this is equal to phi hat of gamma squared times an exponential, and the exponential is e to the 2 pi I n gamma d gamma. Okay. And this is equal to, I'm just going to, so I use a real theorem here, Pascal, but now I'm just going to make a change of variables, and I get this is equal to the sum over k of the integrals over the torus. Just think of going from 0 to 1, which is what I'm doing, of phi hat of gamma plus k, quantity squared, e to the 2 pi I n gamma and gamma. And that, of course, is equal to the integral over the torus of phi, big phi, of gamma, e to the 2 pi I n gamma, d gamma. Well, look at that, we're done. Why are we done? We're done because, let's suppose you have orthonormality. Let's suppose you have orthonormality. So, orthonormal implies left-hand side equals delta n 0. That is to say, it's 0 unless, if n is not 0, and I guess I want to take phi, I want to take phi to be equal to 1. If n is equal to 0, I want that to be 1. Sorry. So this left-hand side is 0, and so what does that say? That says the Fourier coefficients. That says that the Fourier coefficients of phi are all 0 except for the 0 point. Therefore, Fourier coefficients of phi are all 0 except for n equals 0, in which case it is 1. Hark! That means that the function phi is identically 1. Therefore, phi is identically 1, or is 1 on certain. And if you go the other way around, you get the same thing. Same argument works standing in your head, right? To give converse. That is to say, I'm not gonna write it all down, but if phi is equal to 1, then that says these guys are either 0 or 1. 0 when n is not equal to 0. And so that says we've got, these guys are orthonormal. So it's, looks like you get more bang for your buck than you put into the thing, right? But it's pretty easy. There are some interesting things here. What if you look at a respaces? Now, I defined a respaces earlier, and I basically don't want to repeat it, but it's basically a topological isomorphism of a, not basically, it is a topological isomorphism of a orthonormal basis. And so we have a similar result then for that. Fact tau and phi is a Reese basis for V, same V, if and only if there exist A and B such that A less than or equal to phi less than or equal to B almost everywhere on 2. Also not difficult to prove. A little more difficult to prove is the following fact. Tau and phi is a frame for V if and only if, and here's the interesting thing, there exists an A and a B such that A less than or equal to phi less than or equal to B, gee, it looks the same so far, off the 0 set of phi. And so that means that phi could look something like this. So we could have, here we are in 0, 1, and we could have, the function has got to look like this. And if phi looks like that, then little phi, its translates are a frame for V. And this, we proved this a number of years ago with Shidong Li. And there's I'd say a pretty good treatment of this whole little subculture in chapter 3 of this book I edited with Fraser back in '94. But this type of result is used, maybe a lot is overstating it, but it's used with some frequency. And now, basically, it's very popular to think of rank 1 operators and do things with Gabo multipliers and all this sort of, I was going to say baloney, that's right. But this sort of theorem transports itself into that setting too. Okay.
And let me just say that that Christopher Heil PDF, chapter 11 on that is all about respaces, and 12 is about frames. So if you,
I see.
I liked it. I mean, I haven't read the whole thing certainly, there are 100
Oh, yeah, well,
pages, but I liked it.
He's a great. By the way, speaking of Chris Heil, he's coming here next week. He's going to give the, and he's a very good expositor. So if you can make it, I encourage you all to come to his talk. It's at 2 o'clock. We meet, and on Tuesdays. In fact, that'd be a nice assignment for you, and then I don't feel so badly about missing last week, even though I know Enrico gave a great talk, so it's, yeah, Chris got his degree back in 1990 from me, and I only say that because if you come to the talk and you see him, and you don't recognize anyone in the room, he's the one that looks as if he's 15 years old. He's aged very gracefully, or hasn't
Where is
aged.
he now?
He's a professor at Georgia Tech. So another little result I want to mention, proposition, and this is where the scaling equations come in. They play a very big role in all of this, as you expect, because the way we define multi-resolution analysis. Anyhow, there are very down-to-earth equations we address. So let phi be in L2 of R, and assume tau and phi is orthonormal. And also that phi hat of gamma can be written in terms of phi hat of gamma over 2 up to some multiplier, which I'm going to write this way. Oh, this is a little misplaced. But anyhow, let me write it down. H0 gamma over 2, phi hat of gamma over 2, almost everywhere. Then, and we recall we did define these, but I'm going to really talk about them a little more in depth the first part of next class. So assume this and this for some H0 in L1 of the torus. Then H0 is a conjugate mirror filter. And just to refresh your memory, that just means H0 gamma squared plus H0 of gamma plus a half squared is equal to 2, almost everywhere. And essentially, these conjugate mirror filters, also called quadrant mirror filters, they have been around for a long time. They rose most prominently in the speech community, and they're very much used for coding, because, for example, if you take something like a cosine and you translate it by a half, then you're going to pick up a sine if you have period 1. And what you have then is you've got a cosine squared plus a sine squared, and it's sometimes physically convenient to think of that as a low-pass filter, because you're not zeroing out the low frequencies by having them all, say, around the origin, and multiplying them by something positive. But here, you are killing a lot of the high frequencies if it's a sine. And so there's a great study, I mean, this is very, very classical, of design, of filter design. And there are some true Bibles out there. Vaidyanathan's book, I think they probably still use it over in engineering. Was written in the early 90s. It's a very good book from the engineering point of view. But a lot of people have done work on this, and there's a lot of filter design going on. Okay. Okay. I'm actually fading tonight. I think I gave you money's worth on the hour. Would you be upset if I let you go a little bit earlier tonight? You'll be upset, won't you?
He's waiting for it.
I think Hodge would be in tonight, so it's,